Hello and welcome to the WACV 2024 paper presentation. My name is Leon Niggemeier and I am one of the authors of Beyond Self-Attention, Deformable Large Kernel Attention for Medical Image Segmentation. The segmentation of medical images is a complex field. The accurate segmentation can assist physicians in accurate diagnosis and treatment planning. Medical images are captured from various sources like MRI and CT images, as well as ultrasound and classical photography. The image data is, depending on the recording source, 2 or 3-dimensional with multiple channels. Now I will explain two preliminary ideas. The first one is large kernel attention. A large convolution kernel increases the computation cost of a network. Therefore, a large kernel can be constructed by 3 independent operations. The first operation is a depthwise convolution. Secondly, a dilated depthwise convolution, and finally a 1x1 convolution to mix the channel information. Together, these operations construct an equivalent large kernel with less parameters and fewer computations. The second preliminary idea is deformable convolution. Here, the convolution is not on a fixed grid, but instead the network learns offsets that allow the convolution kernels to be applied to a deformed grid. The pixels that are multiplied with the kernel are no longer in the direct neighborhood of the central pixel of the convolution. Our idea is the combination of both approaches. We construct a large deformable convolution kernel from different smaller convolutions. Here, we replace the standard convolution with deformable convolutions. These approaches allow the network to learn a deformable attention map that is multiplied with the input as shown in the figure below. Next up are our network models. We develop different networks for 2D and 3D segmentation. First, a baseline is created that utilizes a max-VIT encoder for feature extraction as shown on the left side, followed by a decoder in the middle that is made from large kernel attention blocks. The large kernel attention blocks are presented on the right side. This baseline model is used for performance comparison with the other models. Then we replace the large kernel attention block with our deformable large kernel attention block in the network to create our 2D network. This is displayed with the red rectangle on the right side. For our 3D version, we build a symmetric network that uses 3D deformable large kernel attention blocks in both the encoder and decoder path. For all networks, we follow the well-known U-shape together with skip connections to propagate information from the encoder to the decoder. We test our models on different 2D and 3D datasets to evaluate the performance. The datasets are, first, the Synapse multi-organ segmentation dataset for the 3D method with volumes and the 2D method with slices. Second, the NIH Pancreas dataset with CT volumes for 3D segmentation. And finally, different skin lesion datasets with 2D images for our 2D network. Now we come to the results. On the skin dataset, we outperform all other state-of-the-art methods in nearly all metrics. The best results are shown in blue and the second best results are shown in red. For detailed 2D results on the other datasets, we refer to our paper publication. On the 3D Synapse dataset, we outperform other 3D networks in the dice score metric. We also note that our baseline method achieves a good performance when looking at performance versus parameters. With a low number of parameters, our baseline achieves good results. For the NIH Pancreas dataset, we refer to our publication. By comparing our 2D and 3D method, we see that the 3D method captures the 3D context better and therefore provides more consistent segmentation results. The 2D method has some inconsistencies between slices. As a summary, large kernel attention allows the generation of a low-cost large kernel that is able to capture long-range dependencies. Deformable convolutions allow the network to learn a flexible deformation grid. Both of our proposed methods achieve state-of-the-art results on multiple datasets. Our code is publicly available under the given GitHub link. Thank you for your attention.